continue to finish up whatever thing that is not been finished yesterday. It's going to be simple for this chapter. It's not something which is very technical, because all the technical thing that you need to know for all the content in chapter 1.4 will be discussed again and again in the subsequent chapters. So the purpose of this chapter 1.4 is just to let you know some simple idea about function. So what we are actually discussing in this chapter is to give you an overall idea, examples or types of function, and show you the shape of some specific function. So yesterday we was talking about linear function. It looks like this. A linear function described by a formula y equals mx plus c. Then we also talk about power functions that looks like this. And then this is the example of power function where the power is a positive integer. It could be also possible for the powers to have a negative integer. Then this is example of a power function with negative integer power. Then this is a shape of the power function where the power is a fractions made up of a ratio of two integer number, and the fractions could be positive or could be negative. And these are the example of the power functions. And then we'll talk about polynomial, the definition of polynomials. And this is an example of a polynomials. And important thing to note is that polynomial is very, very important. You will be going to see polynomials again and again in your next chapter, in the next chapters and next topic. Okay, then you have a rational function, which is made up of ratio of two polynomials. Then the most general forms, well, not but general, a very general form of function we call algebraic functions. Algebraic function is just made up of polynomial function, which is obtained by performing algebraic operations on the polynomial functions. Okay, so maybe let me do some fixing on my WebEx. I think people are going in, coming out, and then there's some noise. I have to close the. Okay, never mind. I think it's I usually when I am dealing with this WebEx things, I can't find my button in the WebEx. It's very difficult and it's very not convenient to use the WebEx. Okay, but never mind. So I'm trying to tell you is that we have these so-called algebraic functions. So algebraic function is a generalizations of polynomial function. So you could have polynomials. You have individual polynomials. Then you perform algebraic operations on these polynomials and then form a new polynomial function. For example, this one is a algebraic function which is formed by multiplying two polynomials. Okay, so then we also have to deal with trigonometric functions in ZCA 110. And the trigonometric function is one of the very important functions that you're going to see. Then we have also an exponential function, which is one of types of functions that will be discussed in more detail. The exponential function and the power function are different, right? The power function is x power n. So let me see if I can write on the screen. I need to have this full okay.
Doctor, full screen, then right click.
Full screen, yeah, I have to do the full screen, but I have to close my touch to adjust the WebEx settings. Very annoying sometimes. Okay, so full screen. Okay, so with the full screen, then I'll recall the, okay, not this one. For the full screen, I need the pencil tool, the pen tool, laser pointer, and pen. So I need a pen. Okay. So this is exponential function, and compare the exponential function to power function. Power function is like this. This is power function where the variable is x. in this case of exponential function, the power is the variable, right? So x is always used to denote a variable, whereas a is usually referring to some sort of a constant. And in the definition of exponential function, the a, which has a name, we call it base, is positive. So the definition of these power functions has to be remembered very clearly. Now, just a reminder before I go on. When you learn mathematics in the university level, it's slightly different, right? Because it's more difficult and it's more advanced. And you have to learn the tricks of how to learn mathematics. It's slightly different. Well, it's very different than the way how you learn mathematics in your secondary school. Now, one very important tricks that I want to remind you again and again is that given any formula, you need to remember and understand the interpretation of every single symbol in the formula. For example, in this case, we are talking about the definition exponential function, which is a raised to the power of x. So in these definitions, a is what we call a is an base, and the definition for this exponential function is the base has to be not zero and it must be positive, whereas x is an independent variable. Then the domain of the exponential function is for real number, all real number, and the graph for this exponential function looks something like this. So it depends very much on what the base is. The exponential function is fully characterized by a single number, which is the base, right? So exponential function have only one sort of parameter, which is a. So if you have a different a, for example, a is 10, a is 3, a is half, then the function would look very different, right? So a power function is characterized by one single parameter. By comparison, say for example, a polynomial, right? A polynomial like this is characterized by how many parameters? Can you tell me? When I say the numbers of parameters used to characterize a polynomial, it means by specifying these numbers of parameters, you can completely describe a function. So a polynomial can be completely described or completely completely characterized by a set of n plus 1 parameter, which is a0, a1, a2, a3 up to an. Right? So give me a set of n plus 1 characteristics of this, characteristics of the set of parameters. So that's, I mentioned this yesterday already. So just tell me what is the values of a0, a1 up to an. So for example, you will say a0 is say 1, a1 is 2, a3 is 1 over 4, a4 is say 1 over say 10. Then this, well, this is a set of 4 plus 1 parameters. Tell me these 4 numbers, 5 numbers, then a polynomial will be completely characterized and the graph will be uniquely plotted, right? Now this concept is very important. Like given a function, how are you going to describe this function? How are you going to distinguish between this function and that function? It is distinguished, the two functions is distinguished by the set of parameters that's described by it. And some functions require more parameter to be characterized. For example, in this case of a exponential functions, only one variable is used to describe it, which is the base, okay? Okay, so then you can also have a situation where the powers of x could be negative instead of positive powers. So if it's a positive power, then it's like this, right? Okay, so these two are actually very similar. So if, for example, if you have a raised to the power of x, right? So say for example, if a is equals to 10, then you have a 10 power x. Now what happens if a is not 10, but instead is 1 power 10? So if a is 1 power 10, then we have 1 power 10 raised to the power of x. And this would be like 10 power minus 1 raised to the power of x. And this is just 10 to the power of x. So, so the relationship between positive power in x and negative power in x is related by this. That is, you just have to take the base and take the inverse of base. Then this graph will be converted into this graph. So we will look at the power function in more detail in later chapter. We have one single chapter that will be exclusively deal with the exponential function. Then you could also have, we're going to meet with what we call a logarithmic function. A logarithmic function and how exponential functions are very, very much related. So later on, you will realize that we will first learn what is the definition of a logarithmic function. Then only we will relate that logarithmic function to the exponential function. So exponential function and the logarithmic function, they are sort of like very closely related to each other. To be more specific, logarithmic function is the inverse of an exponential function. An exponential function is an inverse of the logarithmic function. So this is just an introduction. You're going to see this in more detail. And this is a graph, example of the graph of a logarithmic function. A logarithmic function also has a base. Okay, so logarithmic function is just a specific function that is very important in physics and in mathematics. So we're going to explain and explore exponential function and logarithmic function. Then you also have another groups of function, okay, which is called a transcendental function. Transcendental function are functions which are not algebraic. I think that is what it meant by transcendental function. So in this sense, the logarithmic functions, exponential functions, trigonometric function are what we call a transcendental function. So we have a single big chapters that will be deal with exclusively this transcendental function. Okay, so this is a very simple example. I give you a function, just tell me what type of function is that. Is this a naming, right? So this is obviously an so this is an polynomial function, a polynomial functions which has a degree of 5. Okay, and this is what is this a power function or is it exponential function? So this is a power function. So this is a power function where it has a base of 7, and then this is an exponential function. Okay, exponential function. Okay, exponential function where the z is the variable, right? So here x is used as a variable, whereas in this particular example the z is the variable. So let's remind you, people who might get confused, when you see x, then you normally think x is a variable. When I change the symbol of x by z, then you got confused, but you should not. For example, if I say, okay, this is a function, h is a function of x equals to x power 7, then you can recognize that x is a variable, and this is an exponential function which is raised to the power of 7. Exponential and c power.
Doctor.
Yeah, am I right? Correct? No?
The shouldn't exponential function and power function should be the same, and exponential function, the variable should be the power, right?
Okay, so let me go.
This one looks more like just a normal polynomial without any other variables.
Okay, so let me come back to the exponential. So for exponential function, you have a base raised to a variable, right? So a base raised.
But the base is, well, this one the base is
Okay,
not constant, right?
exactly. Now I'm very happy because I make stupid mistake. I confuse between exponential function and the power function. So this is not a power function. This is an exponential function. Exponential function which has a base a equals to 7 raised to a power of x. So this is an exponential function. And this, which h of function of x equals to x power of 7, if I write this, change the variable of symbol of z into and x into z, this is variable z. So this is a variable raised to a power of 7. So this is what we call a power function. Okay, now I do not pretend that I make no mistakes. I admit that I make stupid mistake. I confuse between the exponential function and a power function, right? So you don't learn. Well, this is my stupid mistake. So I make confusions, and when you study, you try not to repeat my mistakes. So try to train yourself to make a distinction between the exponential function and a power function. Okay, so a power function is a variable. A power functions like this is a variable. So here is a variable that's raised to n power, which is not a variable. Whereas for exponential function, you have a base, which is 7, raised to n variable. So that are the two distinctions of the two variable function. Okay, so I make stupid mistakes, you don't, right? So if you make stupid mistakes, you would be deducted your mark in exam. I won't, right? So now this is an example of exponential function and power functions, and you can have to realize what is the power and what is the base. Here, the exponential function has a base of 7. Here, you have an power function which has a base of 7, of whatever. Here is power of 7. Here is an exponential function with a base of 7. This is an exponential function which is raised to the power of 7. And this is an example of a trigonometric function. Okay, so the next thing we want to talk about is a very simple concept called increasing function and a decreasing function. So if you have a function, so usually you plot the functions on the xy axis. Then you try to make x, that is the variable, to increase from the left to the right. So when you change the functions, when you change the variable of x, right? So when x is changing from, say, from somewhere, say 9 minus 10 to a direction which is positive to somewhere which is on the right of minus 10, then the values of the function y will change as well, right? So when change in x is happening in the increasing directions from left to the right, then what happened to the values of y? So if you change the values of x from a smaller number to the larger number, which is from left to right, and if the function of f sort of like increase, then you would say that the function is increasing, say for some range of x. Now, if you have a function where when you change from left to right, the function is going down from x when it's changed from left to right, then we say the function is decreasing. But mathematics is a very specific and very precise language. You cannot just simply say a function is increasing. If you say a function is increasing, what you mean is that the function is increasing all the way for all its domain. That is what you meant when you say a function is increasing. When you say a function is decreasing without saying anything about what range of x it is decreasing, it would mean that the function is decreasing for all the domains of the function. And sometimes this could be wrong, right? For example, you could have this situation. So in this case, the function, is it increasing or decreasing? No, you cannot say this function y equals x squared is increasing or is decreasing, because when you say it's increasing, it means when you go from left to right, the function will always goes up when you say it is increasing. But it's not true, right? When you go from the left, say from here, from this value to the right, say from this point to this point in x. So when x is changing, the values of y is actually dropping when x is increasing from the left to the right. So the function is actually decreasing when you go from negative infinity towards 0. But once the x is larger than 0, then the functions is actually increasing. Right? The function is increasing when x is larger than 0. So you cannot say this function is increasing or decreasing. You have to be very specific. You have to say the function y is increasing for x, which is less than 0, and y is y is decreasing for x, which is in the negative direction, and y is increasing in the domain where x is positive. So whenever x is positive, the function is increasing. This statement says, as long as your x is larger than 0, when you go to the right from the left, your function is always increasing. So what I'm trying to tell you is that when you want to describe whether a function is increasing or decreasing, you have to be very specific in mentioning what range of x is the function increasing, what range of function is the function decreasing. Right? So without mentioning the range where the function is increasing or decreasing, by just mentioning is increasing, it would mean it's increasing all the while, which may or may not be correct in general. So this is example. Another example, this is a case where the function is always increasing. The function is always increasing, right? Okay. So so it's actually quite easy to understand the definition of a function, whether it's increasing or decreasing. So I give you a function like this, then you should be able to tell whether the function is increasing or decreasing. For example, let's just look at y power of 2, 3. So this one. So in this case, the function is decreasing when x is negative, and the function is increasing when x is positive. The function is always increasing for all its domain. So this case, the function is always increasing for all the domain. So this example, the function is always increasing. Okay, so I wouldn't expect any difficulty for you to understand the definition of whether a function is increasing or decreasing. Okay, so then the next thing I want to talk about is a very simple concept, which is called a function that has an parity. Parity. So parity is this P-A-R-I-T-Y. Okay, so parity. The function could have positive parity or could have negative parity. So positive parity is synonymous to saying it's even. Okay, a function which has negative parity is equivalent to saying the function is odd. So the function is odd means it has negative parity. The function is even, it means it has positive infinity. So what you mean by a function which is positive in parity or negative in parity is just very simple. As long as a function fulfills this condition, but when you reverse the sign of x in the independent variable, and if in the process of inversing the values of x to negative x, if the sign of the function y remains the same, then this function is said to be positive parity or is even. If a function becomes a negative in sign, when you revert the variable x to negative x, then the function is said to be odd. So a simple example is this, right? So when you have a function fx equals to x, so in order to say whether it is positive or negative parity, what you do is that for all values of x in the expressions on the left hand side, you just revert the sign. Whatever you see an x in this formula, you just put a sign in it. So here you have x, and then you replace x by negative x, and then this will become negative x. Okay, then you have a square. So I'm just rewriting the equation fx equals to x squared by replacing all the expression of the symbol x on the left by negative x, right? So x become negative x. Here, the negative x become negative. So when I go from left to right, I'm doing nothing. I'm just performing an operation of replacing the symbol. When I replace the symbol, this become x squared. Okay. So then this is the expression of f of minus x, and it is x squared. And the original values of the function if f of x is x squared. So what you do is that you compare this to this, right? So you compare this to this. So you find that the f of minus x and fx, they are exactly the same with the same sign, which has positive. So we say that x squared is having a positive parity. An example would be this. Another example would be fx is equals to x squared plus 1. Then you ask a very simple question. Is this function x squared plus 1 odd or even? So in order to do that, you just carry out this operation, replace x by minus x, then you see that when you do that, you just rewrite the whole equations again. When you see x, you replace it by minus x, then this is minus x squared plus 1, and what you got is x squared plus 1. So you have f of x minus 1 equals to x squared plus 1. Then you compare, right? CF means you compare the equation or expression after you have performed the operation of replacing x by minus x. Compare it with the original function, which is x squared plus which is equals to x squared plus 1. So you will compare these two, and then you would then realize that f of x is just equals to f of xx, right? So the sign, relative sign between f of x and f of x minus x is plus. So they say then the function of x squared plus 1 is even function. Now this is very simple as well, right? So so originally you have function equals to this, then you carry out an operations, then what you get is f of minus x equals to minus x. Then you compare this expression to this expression, compare, then what you got fx equals to f of minus x with a minus sign, which is equals to x, right? So this is a conclusion that you would obtain when you compare the expression on the left and the expression on the right. Then you say that f of x is having a relative minus sign with respect to f of x. Therefore, whoa, wait, that just press some wrong thing. Okay, so so therefore you would say f just say f of x is equals to negative f of negative x. So this is a conclusion that you can obtain after you replace the expression of x by minus x. Therefore, this is that symbol saying therefore fx equals to x is odd. Okay, so next question is, let's try this. You have a function of fx equals to x plus 1. You carry out an operation of replacing all the x by minus x, then you get this, right? So you replace the x by minus x, then when you see x, you replace it by minus x. That is, you replace this by minus x, then 1 is just 1. So you have this expression of equals to 1 minus x, and you compare with the original functions. What is original function? The original function is equals to 1 plus x. So can you tell me, so this is x of minus 1 and this is xx. Now f of minus x is 1 minus x. Fx is 1 plus x. So what is the sign between this expression and this expression? Is a sign plus or is a sign negative? Anyone? What is the sign? Should be negative or should be positive?
Negative.
Negative. So if you make this fx to be negative, it become x minus 1, right? So if you take negative, it become x minus 1. So you compare x minus 1 with 1 plus x. So if you say it is minus 1, this is what you say, okay? If you say this is f equals to this one, so let's look at what is the f of minus x. F of minus x is 1 plus x. What is minus x f of f? So this is fx by definition is x plus 1. So it's x plus 1. So someone say the left hand side is the negative of the right hand side. So is this a correct statement? 1 minus x is equal to minus bracket of x minus 1. This is equal to minus x minus 1. So is 1 minus x equals to minus x plus 1? Yes or no?
No.
No. Okay, so it could not be a negative sign. Could it be a positive sign? If it's a positive sign, what you mean by that is that if fx is a positive sign, then this statement is written explicitly as x minus 1 is 1 minus x. I think this is the x of minus x, and fx is x plus 1. Then could it be a positive sign? Could.
Also.
It's not also, right? So it's not positive, it's not negative. So is this function x plus 1 odd or even?
Is it neither?
Yes, it is neither. So it is not odd, it's not even, it has neither. It has no parity. So not all yeah.
Both
Question?
even and odd function need to be symmetrical.
If it's an odd function, it means it is odd. If it's even, then it is symmetrical. Well, it depends on what you mean by symmetrical. It's symmetrical with respect to the y-axis. Yeah. So this is an example of an symmetrical function. And function which has an even parity is symmetrical with respect to y, but not symmetrical with respect to x. So you reflect the function about the y-axis, then the function looks the same. Then this is an symmetrical function, which is an even function. A function which is odd would be like this, right? This is an even function, an odd function. Odd function is anti-symmetrical when it's reflected about the y-axis. So this is an example of an, let me see, this is an odd function, okay? This is an odd function, so x plus 1. X plus 1, is it an odd function? Is x plus 1 an odd function? So the answer is not, right? The answer is that this is not an odd function. So it is not symmetrical when it's reflected about the y-axis. Okay, so to be very specific, when the function is even, then it is symmetric when you reflect it about the y-axis. Okay. Then in this case, y equals to x is an odd function. So the odd function is not symmetric when it's reflected about the y-axis. Okay, but it has other symmetric operations. So it's very easy to look at a graph and tell whether a function is even or odd. So when you have this function like this, obviously when you look at it, you know that this function is even. That is, when you replace x by negative x, then the values of y is the same, right? So here, sometimes it's not easy to see. For example, if you look at this one, say this is 1, y. So for example, if this is 1 and this is 1, right? So when you make it to become minus 1, then the values of the function is here. It is minus 1 and this is 1. So when x equals to 1, the function is 1. When x equals to minus 1, then the values of function become negative of 1. So this is obviously an odd function, but this is not, right? So when you reflect 1, say from here, and 1 to become 1, then the values of the function change from, I think, from 2, this is 2, to 0, right? So for this particular example, when you replace x equals to 1 by x equals to minus 1, the values of y change from 2. Again, I pressed the wrong button. Okay, so do it again. So here, if x equals to 1, oh, okay, I have no more time, maybe I won't do it. But just to let you know, this is an odd function and even functions. So whatever graph that's given to you, this one is obviously an even function. This is obviously an odd function. So I think for odd functions, it has a symmetry, which is what called reflection symmetry with respect to 0. That is, the graph, if is reflected about the origin, then you get the graph. So an even function is symmetric with respect to reflections about the y-axis. Whereas for an odd function, it has a symmetry with respect to the reflections of the function about the origin point. Okay. But anyway, this is the definition of an even function and odd function. It's just like any function that fulfills this condition is called even. Any function that fulfills this condition is said to be odd. Right? So a function that does not fulfill neither of this condition is neither even or odd. So a function is not always having an parity. Okay, so when I ask you, is it even or odd? The answer is neither. So I like to to play tricks with students. I always ask questions that have no answer. So the answer is wrong, whatever you give, right? So it is not odd, it is not even. So be very smart, right? In mathematics, you have to be able to think out of the box. Sometimes people thought that I'm given a formula, then I must be able to derive answer from the formula. But if the formula itself is wrong, or your understanding is wrong, whatever answer you derive there will be wrong. So if a function has no parity and asks you what is a parity and you try to give me an answer, then whatever answer you give will be wrong, right? So how do you avoid that? You can avoid that by understanding properly the definition. If you stick to the definition, then you would mostly be safe. Hey, so today we have take up another sessions for this. So I'm sorry for my delay during this early stage of the lecture. So we are going to finish our lecture for this morning.